wanted to do an introductory series on cutting operations on the mini lathe. Some of you may have gotten mini lathes for Christmas or recently, and I'd hoped to do this a little bit earlier, like prior to Christmas, but didn't get to it, but I'll do it now. In a facing operation, we cut sideways across the face or the end of the round piece of work. This is 1/2 inch diameter aluminum. And it's been cut on the bandsaw, so you can see it has sort of a rough finish on it right now. And part of the purpose of facing is to convert that rough finish into a nice smooth finish. I'm going to use a 3-jaw chuck for this operation. I like to use the 3-jaw for most of my work just because it's quick and convenient. I also like the 4-jaw, but I save it for things that I can't do with the 3-jaw. And I'll be using the LittleMachineShop.com. It's a model 5100 lathe. And this lathe, if you aren't familiar with it, it's pretty much the same as the other mini lathes, except it has a larger spindle. It takes a 4-inch chuck as standard rather than 3-inch, which is standard on most of the other mini lathes. A quick comment in passing in case you see it and are wondering about it, but I've replaced the plastic safety shield that goes over top of the chuck with this small aluminum one. The plastic one that comes with the lathe tends to get in the way out here when you're trying to do certain operations if you're working up close to the chuck, or even more so if you're working on a faceplate. The real purpose of the plastic guard is to prevent you from accidentally turning on the machine when you have the chuck key still in place in the chuck. And this little guard will do the same thing. And when it's in the up position, of course, the lathe cannot be started. Take our piece of aluminum stock here and put it down in the jaws. Usually I like to take a little brush and clean up the jaws, make sure there's no chips or grit in there that could keep it from seating properly. And for this operation, since all I'm going to be doing is working on the end here, I want to set it pretty far back in the jaws. And of course, the farther back in there you set it, the more rigidity you get. But generally you want to avoid having the work stick out more than 2 or 3 times the diameter, or it will start to flex a little bit. It may not be much, and you may not even be able to see it flex, but when you're talking about dimensions of 1/1000th of an inch or a few thousandths of an inch, even a little bit of flex can affect your work. Now this mini lathe, I've equipped it with a quick change tool post, which I really like. And I strongly recommend that you get one if you can, or as soon as you can, because they'll really make everything you do on the mini lathe a lot easier, and you'll actually get better quality work because of the ability to adjust the height, as we'll see. But I have actually 3 different tools here of different types, and I'll just show them to you briefly. The one on the right here is one that I ground on the grindstone from high-speed steel blanks. This one is a prefabricated carbide tip that goes in a special holder. And this one on the end here on the left is actually a high-speed steel insert. These are pretty nice. I like to use high-speed steel on aluminum. It usually does a better job of cutting, at least on a relatively low speed lathe like this. And carbide works great on steel and harder materials, but usually doesn't leave as good a finish on aluminum. But we'll try maybe one of each and see what happens, just for comparison. Now I'll start out with my shop ground high-speed steel tool, and it's a very simple grind. I have a website, minilathe.com, and if you look at tool grinding, it will show you the basics for grinding this particular type of tool, which I use a lot, and someday I hope to get around to making a video on that. Now, of course, the big advantage of the quick change tool post is the height of the tool is already set. I set it previously, and the tool stays with the holder so that once you've got the height set, in the future when you go to use that tool, you just drop it in place and then lock it with this cam locking lever, and it will be at the correct height. But I'll show you what happens with the facing operations if it's not at the correct height. A facing operation, like most operations, it's important that you have the tool right at the center height of the lathe, which is to say that's an imaginary line that goes from the tailstock to the headstock, and would be the center line through your workpiece. So you want your tool right on that center line. When you get ready to make a facing cut, you have to have some way to lock the carriage down. And there's basically two ways to do that. One is to use the half nut lever and lock the carriage down to the lead screw, but of course you have to make sure the lead screw is not turning. And the other way is to have some sort of carriage lock, and in this lathe I've built my own, which I'll show you in a minute. But let's talk for a minute about the locking the half nut lever. Now back here on the back of the headstock, there's a lever, a 3-position lever that controls the rotation of the lead screw. But in this case I want the lead screw in the neutral position. So if I turn the lathe on, if you look down here, you see that the lead screw is not turning. Spindle's turning, but the lead screw is stopped. And that's the situation we want, so that we can lock the carriage down to the lead screw and it will hold the carriage in place. Now ordinarily when the lead screw is turning, when you engage the half nut lever, you can just put a little pressure on it, and as the lead screw rotates it around, it'll lock in. But when it's not rotating, you may have to wiggle the carriage back and forth a little bit as you're engaging the half nut lever, so that the threads on the half nut lever engage with the threads on the lead screw. The purpose of locking the carriage to the lead screw is that the cutting forces otherwise could push the carriage back away from the work. And instead of getting a flat surface across here, you'd get some sort of a cone-shaped surface as the carriage drifts away from the work. Now I've equipped my mini lathe with a shop-made locking lever here that also locks the carriage to the ways, and that's actually preferable to using the lead screw. So if you have an arrangement like this, that's what you want to use. If you look on the internet, you can find lots of plans for different ways of doing that, and the only difficulty is that a lot of them, maybe most of them, require the use of a mill, or if not a mill, then some heavy-duty filing to accomplish it. Okay, now I'm about ready to begin the cut, but you want to position your workpiece, and you can now use the compound hand wheel to move the tool forward and backward if you need to adjust the point at which it's going to cut into the work. But you want to take a fairly light cut, no more than say 10 thousandths or so. If you take a little bit more, it'll probably still work, but if you get to the point where you're taking 30 or 40 thousandths, that's probably going to be too deep a cut and the lathe may stall, or you get a lot of chatter. So I'm going to back this off. One way you can adjust that if you're not confident with it is bring the tip of the tool up until it just touches, then come out with the cross feed, and then use the compound hand wheel, and you can just dial in about 10 thousandths or whatever you're comfortable with. Now it's not going to be exact because the compound typically is at an angle, so the depth that you read off of the compound hand wheel usually will not be the exact depth that the tool is going to move in, unless your compound happens to be parallel with the ways of the lathe. But with that set, let's go ahead and turn the lathe on. And now I'm going to use the cross feed or cross slide, and we'll just turn that slowly by hand and make our facing cut. I don't have a tachometer, so I don't know what the actual RPMs is, but I have the dial set here on the control to about, if this is the 6 o'clock position, then this would be about the 10 o'clock position. Let's take a look at our result here. You can see that the surface is basically flat, but there's a little nub there in the center. And that nub tells me that my tool, the tip of my cutting tool, is either a little too high or a little too low. And usually, with experience, you can tell from the shape of that nub whether it's high or low. And if it's low, that nub will usually be cylindrical. But if the tool tip is a little bit above the center, the nub will end up being more of a conical or sort of a mountain or cone shape. So in this case, it looks like it's, my guess is, and I can't see too well, but it looks like it's a little bit low, and I'll use that as my starting assumption. This is where an adjustable tool post or a quick change tool post is really handy. I'm going to just loosen this locking nut here. Now I'm going to unlock the tool, then turn this ring and that will raise the tool up just by a few thousandths. I don't know exactly how much, but one of the interesting things about a facing cut is you can actually use it as a way or a gauge to determine if the tip of your tool is on the center line of the lathe. If it's not, it will leave a little nub. But if you get it right on the center line, then you won't get that nub there, and that's what we want, no nub. Okay, with the height adjusted now, we'll take another test cut. And it looks like I got rid of the nub. Let's take a closer look. Alright, now as you can see, there's no nub in the center, and that's the way we want. So if you get a nub, you have to play around with adjusting the height of your tool, either higher or lower. Now if you don't have an adjustable tool post, you can get yourself a set of automotive feeler gauges, and of course these are all, if you're probably familiar with them, but they are all marked with their thickness, usually in thousandths, but they may also be marked in millimeters as these are. Anyway, you just pick a few of these, usually starting with the thicker ones, and then place one or two or three or how many you need to get the tool right on the center height of the lathe. Just take your stock tool holder and put your tool bit in here, and then just tighten it down finger tight. You can bring it up to the work and see approximately where it falls, you know, whether it's too high or too low. Now this is a 5/16 inch tool blank, so it happens to be a little bit low. I could have started with a 3/8 inch tool blank, and it might have been a little bit too high. I like to use smaller tool blanks. In fact, I often use a 1/4 inch just because they're quicker and easier to grind, less metal to remove. And even 1/4 inch will work fine on the mini lathe for just about anything. So next you can do a test cut and see what kind of nub you get. After tightening my tool bit in the tool holder, and I'll lock down the carriage, now I'll take a test cut to determine whether the tool is too high or too low. And as you can see, we get a little stalk there, and I could see clearly that it was too low, so we'll put a couple of shims under there and try again. A trick you can use that may help you speed up the process is to take your digital calipers and measure the diameter of that little stalk. You need to make the stalk long enough that you can get the tips of your calipers on there though. Alright, and it's reading about 68 thousandths. I'm going to try using a stack of shims that are half of that, or 34 thousandths. That should get me pretty close. So for my set of shims, I've chosen a 22 and a 13, so that should give me 35. Should put me pretty close to center. Now we'll just loosen up the tool, and we'll put these shims underneath and then tighten it back up. Alright, so we'll tighten it up now. And now we'll do another test cut. Okay, well that worked out pretty well. Looks like it got us very close to on center, and that may be all we need. Let's do one more pass with higher spindle speed. Alright, that looks pretty good. Now that we've seen what it looks like with the tool a little bit too low and the tool right on center, let's just for the sake of demonstration here, I'm going to intentionally raise the tool up above the center line, and we'll take a cut and see what we get. Now you may even find if your tool is too high, the nub in the center will actually prevent the tool from trying to go past the center, and when you're turning the hand wheel, you'll start to feel a lot of resistance there. So if you feel resistance as you're approaching the center, that's a good indication that your tool probably is too high. But if we zoom in now and look at close-up, you can see that there's a very definite cone shape there. So whenever you see that, that's an indication that the tool is too high. But using this knowledge about these little nubs that form here on a facing operation, you can take advantage of that as a method to set your tool height. And in fact, the method I use most often for adjusting my tool heights, I'll just take a piece of scrap aluminum typically and make a couple of facing cuts and tweak my fine adjustment here on my tool height until I get a nice smooth face across there. And then I lock that nut in there, and that becomes my tool height. So I adjusted my tool holder to bring that tool height right on center, and that's what a nice clean facing cut should look like. One more thing you may wonder about if you're new to this is what angle should the tool be at relative to the face of the work. And if you had the tool squared up against the face, you wouldn't get a nice clean cut because the edge of the tool would be just rubbing against that surface. For best results, you'll want to use a tool with a slight radius on it, and I like to use an angle between the tool and the face of the work of somewhere between about 5 and 15 degrees. But you can experiment and see what you find in your own shop. For this next test, we're going to just do a basic facing cut, but instead of the hand ground high-speed steel tool, I'm going to use this factory-made carbide insert tool. It's got 3 points, 120 degrees apart. Well, actually, here again, it's not too bad. I think we got a better finish with the high-speed steel tool. This shows a little bit of surface roughness. That's been my experience with the carbide tools. They work pretty well, but they don't give you quite as nice a finish on aluminum. This time we'll take a cut using the high-speed steel insert. Let's zoom in and take a look. Well, that did a pretty nice job, so I think you can see any of the types of tools will work all right. I think the carbide tool maybe gave a little bit not as good a surface finish, but with some experimentation you might be able to get good results with that. Now, one thing I didn't mention is particularly with aluminum, I often use cutting fluid, and I like to use Tap Magic aluminum brand. But it keeps the chips from welding to the tip of the cutting tool, which can sometimes cause problems. And in fact, I just noticed that on this carbide tool here, it looks like there is some stuff welded to that tip. I think maybe the message here is that 6061 aluminum is a pretty forgiving material, and even if your tool geometry is not optimal, you can still get reasonably good results. But for the best results, you'll want to use a tool with a slight radius on it. For those of you who are steel workers, I'm going to take this gnarly piece of steel. It was given to me by a friend. It was cut from a long piece of bar stock. So I don't know anything about its history other than it sat in a barn for many, many years. But I think it's probably some sort of some variety of cold rolled steel, and it has a saw curve here where I started to cut it and then changed my mind for some reason. But we'll go ahead and do a facing cut on that and see how it looks. I'll turn the speed down, see if I can get rid of some of that chatter. But let's try turning the speed back up and taking a shallower cut. Well, that's not too bad. It actually feels quite smooth. So just to show that you can do this with steel, there we go. Now, one other factor that's really pretty much a routine part of a facing cut is when you're done facing, you end up with very sharp edges along here. And if you're not careful or not fully aware, you can cut yourself badly when handling this material. Doesn't matter whether it's steel or aluminum, but steel is more likely to cut you. The harder the material typically leaves sharper edges. So I always like to touch it up with a file, take that sharp edge off, or use a tool, which I'll show you in a minute, but we'll first do it with the file. When working in the tight confines of the mini lathes, I'm sure most of you know, you need smaller tools than you would on a big full-size lathe. But these are, I guess, 4-inch files, and I like both of them. They're made by Nicholson. But this one I find particularly handy because it has this sort of tapered blade that comes to a point, or nearly a point, so it's able to reach into spaces that you might not be able to get access to with a wider one like this. Many years ago, I had a picture on my website showing me filing work like this, and a viewer of my website sent me an email, which I'm actually quite glad that he did, and said, you know, that's a bad way to use a file because your hand is extending over the rotating chuck. So the trick here is to hold the handle of the file in your left hand, then you can hold the tip for more control in your right hand, but that way both of your hands are out here, out of the way of the chuck. Now you're still working pretty close to the chuck, obviously, and you want to be real careful. By the way, you should always have a handle on your file, so you can get them cheaply, and they last pretty much forever. But they can save you from a really serious injury if the file were to be pushed back, or the tang of the file pushed back into your palm. You'd be looking at some serious surgery. So definitely invest in some handles, and you can get all kinds. Just touching up this edge or breaking this sharp edge, we can use a pretty slow spindle speed. You don't need much speed at all to do it, you know, maybe 100 RPM. So we'll just take the file like so, and you can see it just removed a little bit of metal there on that sharp edge, and that's all we need to do. And now it's much safer to handle that. But an alternate way to do it is to grind yourself a little tool similar to this one, and you can use that for the same purpose. Just as with the facing cut, we want to lock the carriage down so it's not going to move during this beveling operation or chamfering. So, and again, we can use a pretty slow speed for this, and it really only takes a second. Just barely touch that tool to the work, and the job is done. If you want to, you can go in a little deeper and actually put a chamfer or a bevel on that work. So here's what we have now, and of course it's much safer to handle now with that sharp edge gone. And if you stuck this away in a drawer somewhere and forgot about it, you reach in there, you know, a month later or a year later, grab that piece of metal, you can get cut without expecting it. So that's, often when I have a piece left over, and I'm not going to use it for a while, I'll just touch it gently with a file before I put it away in the stock drawer. Well, just for fun, to show that it can be done, here's an odd-shaped chunk of brass that I acquired from a junkyard probably about 15 years ago, and it was sort of a sharp metal stake, some sort of ground stake used by utilities, I guess, for some purpose. But anyway, it was a nice piece of brass, and I bought it, and I've used it for various projects in the years since then. But it had these sort of blades on the side, which I sawed off with the bandsaw. But this edge, or this face here, has never been faced, and so I thought it would be interesting just to put a facing cut on that and see how it goes. We're getting a little close to the capacity of this 3-jaw chuck, and you got to be real careful that you aren't opening the jaws so wide that they don't have any grip on the scroll inside, and they're going to come flying out. So anytime you're going to grip something like this that is fairly large compared to the chuck, it's a good idea to test your jaws and make sure that they're not near the end of their range where they might come loose. I think I'll set it back in there a little bit farther just to get the maximum gripping power of the jaws. And I want to tighten it all three scroll positions here. Make sure that's pretty tight. This is a heavy piece of material. You definitely don't want that working loose. And always check. Sometimes your work will get skewed in there. Good way to check that is as you're tightening the jaws, rotate it gently, and if it's skewed at all, you'll be able to feel, or hopefully be able to feel, that it's not locking up evenly and smoothly. So another good thing to check, especially on a heavy workpiece like this. Alright, let's fire the lathe up here and see what this does. What you hear there is the cutting tool hitting these ridges on the edge, but the actual cut looks like it's a little deeper than I want to take, so I'm going to back the tool off a little bit. You can hear that it's still not making contact all the way across. It's looking good. I'll take one more pass. Speed it up just a bit. There's still a tiny little stalk there, which tells me that the tool is a little bit low. Just to give you an idea of the size of this little nub here, this is a number 80 drill bit, which has a diameter of 13.5 thousandths. So you can see that the little nub there is really pretty tiny, probably around 10 thousandths or so, maybe a little larger. Kind of makes me wonder how they make these tiny drill bits and cut a helix into them. Something to think about, I guess. I wanted to comment on the cutting speed, or the spindle speed to use when doing a facing operation. Now the interesting thing about a facing operation is as the cutting tool moves in from the outside diameter to the inside diameter, the speed at which the tip of the cutting tool traverses the material is faster out here at this larger diameter, and it actually becomes slower and slower, and it approaches zero as the tool gets near the center. So if you stop and think about it, you know, the speed at which a point on this disc moves past the tool, the farther out on the disc that you get, the faster it moves. So on a small workpiece like this, it's probably not too significant. If you imagine an industrial setting where you're turning, for example, a large wheel for a railroad steam engine or something, you know, back in the Industrial Revolution days, on the outer edge of the wheel, the metal would be moving past the cutting tool very, very rapidly. Now, of course, they turn those things at very low RPMs. I believe I've read that there are lathes, mechanical type lathes that were used historically that would increase the rotational speed of the work as the tool moved inward on a facing operation. And of course, nowadays, a lot of this type of work would be done on a CNC or a computer-controlled machine, in which that type of speed compensation is pretty straightforward to arrange and build into your programming. But for the type of work we do on the mini lathe, the speed isn't very critical at all, and I usually start out, you know, around 800 RPM or somewhere in that range, and either speed it up or slow it down depending on the hardness of the material and other factors. But if you look and listen, you can tell quite a lot about what's happening and whether the speed is working well or not. And of course, with the variable speed control, you can make compensation on the fly. And if you really wanted to get tricky, and I've tried this a few times, if you had a relatively large diameter workpiece, say 4 or 5 inches, you could actually change the rotational speed like the automatic machines do, except do it manually. So something you might want to play around with. But the good news is that the mini lathe, for the type of work we do, it's not a huge factor. So find a speed that works for the material and the tool you're using and go with that. Well, that wraps up our tutorial on facing operations. If you like this video, I'll be doing some more on other basic lathe operations on the mini lathe. And if you subscribe, you'll get a notification when those come out. So thanks for tuning in, and we'll see you next time.